Hello everyone, welcome to lab 4. This lab will discuss about discrete Fourier transform. So real world signals are analog signals, that is continuous in time, hence infinite values. Since computer cannot handle infinite values, it needs to be sampled in time domain. To get frequency spectrum of sampled signal, we perform discrete time Fourier transform, that is DFT. But the spectrum of DFT is also continuous and needs to be sampled. So sampling in frequency domain leads to discrete Fourier transform, that is DFT. So here what we see here is the DFT formula. Now if we replace omega with 2 pi k by n, where n, capital N, is the length of the samples and k is the kth index, at the kth index the frequency we want, then this formula becomes DFT, discrete Fourier transform. Finding pulse period with DFT. First one, moving averages the signal to smoothen it and remove high frequency noises. Then one takes the DFT of the signal and finds the k index for which magnitude response is maximum. K index means this k value. The first peak is taken in magnitude response. The corresponding frequency for a k index is k index, k into sampling frequency by length of signal. The pulse rate is obtained as 60 into that pitch frequency as computed above here. So this is the DFT spectrum showing periodicity, repetitions, and this is just showing one period, the spectrum. And now we have DFT spectrum of a moving averaged signal, that is the signal has been moving averaged in time domain. Now we have the Arduino implementation code. So here we have all the initializations, and the main part is here is we'll have two matrices. Those are in real we have one matrix, that is the DFT matrix, but since Arduino cannot handle complex number, it doesn't have any library, we'll take two separate matrices, one for real matrix and one for imaginary part. So we'll initialize them here. The real as cos 2 pi kn by capital N and imaginary part as minus sin 2 pi kn by capital N. Then we'll moving average the signal, and at this part here we'll multiply the DFT matrix corresponding matrices with the moving averaged signals, and we'll obtain the DFT, discrete Fourier transform matrices, real and imaginary, and then we can plot the magnitude spectrum here, and we can also find at what k index, at what first k index the maximum magnitude spectrum we are getting, and then we can print that. So coming to the MATLAB code, which is very similar, the only difference is in MATLAB we can have one single matrix, and we have in here we have initialized it as e power minus 2 pi j k z by r, where z is taking the place of n and r is taking place of length of signal. And since MATLAB handles complex numbers very well, we don't need to separate cos and sine, and here we can do the DFT matrix into signal multiplication and we can get the DFT. So results, these are the results obtained in MATLAB. This is our original signal waveform, this is a signal waveform with moving average, this is a normalized DFT with without moving average, this is with moving average, that is the signal has been moving average in time domain. And this is the beats per minute pulse rate that we obtain in MATLAB, which is 60 bpm for a moving average window of 7, and without moving average it is 140 bpm. With autocorrelation function in Arduino, we found it to be actually 71.43 bpm, and with the DFT in Arduino we found it as 80 bpm. So the error obtained is 11.99%. I'll show you the pulse rate found with autocorrelation function. Yeah, so pulse rate with moving average of into 10 is 71.43. And here are the different blocks. We have divided the signal into blocks, and this is the pulse rate of each block. So this is all about lab 4. Thank you.